Hi, welcome to my talk, Leveraging the Power of State Machines in Swift. Who am I? My name is Frank. I'm based in Montreal, Canada. I've done iOS mobile consulting for almost a decade, and now I'm a full-time iOS corporate trainer through a company called School of Swift. School of Swift is an online organization that helps you and your team learn new skills. We deliver interactive workshops on all sorts of iOS topics, and most workshops are as short as half a day. This way, you can learn something new without jeopardizing your development schedule. We have a bunch of public workshops coming up on topics like accessibility and async await, and we can of course schedule private sessions for your team. We're located in Canada, but we can accommodate pretty much any time zone. So even if you're in Singapore, we got your back. If that sounds interesting, check out schoolofswift.com. And of course, you can reach out if you like this talk, or if you don't like this talk, if you think I'm wrong. You can always find me on Twitter, @Frankacy. My DMs are always open. You can tell me in the conference Slack, where I'm also @Frankacy. And you can email me at hello@frankcourville.com. I'm great at responding to tweets. I'm awful at responding to emails, and I hope this slide communicates my preference. All right, let's get to the good stuff. In this presentation, we're going to talk about state machines in Swift, what they are, how to build them, and why they're useful. We'll learn how to draw state diagrams, take those state diagrams and translate them into Swift, and we'll also see some advanced applications of state machines in our code. But perhaps most importantly, why should you care? The reality is that state machines are everywhere. They are in our code and honestly in our daily lives. Things like the turnstile that you use to take public transit or the cruise control in your car can absolutely be represented by state machines. Even like a simple traffic light is a great example of a state machine. But before we get into all that, I want to talk about something which at first glance will seem completely unrelated, but I'm going to ask you to bear with me. I want to talk about UIKit coordinators. For those of you who are unfamiliar, a UIKit coordinator is an object that controls the flow in an app. This was popularized by Sarosh Kanlu a few years ago. And the idea is that they're like a programmatic storyboard. It strings together many view controllers, and they define the valid flows a user can take through a certain feature. Now, as a freelance developer, I've worked on many different projects. I've seen this pattern again and again. It's something I use myself. It's like my go-to pattern for UIKit. However, I've always felt a bit uneasy about using coordinators. Because the reality is when you look at a coordinator class, there are always these questions that come to mind, right? Like, how can you tell what the order of the view controllers are? There's nothing in the code that really communicates this to you. You kind of have to piece it together yourself. It's also not clear how each of these view controllers interacts with the coordinator, right? Like often it's going to be split up between multiple files, and you have to kind of like search the whole landscape in order to figure out what's going on. And I find perhaps most damning of all this is like, how do you even test this? How can you be sure that 1 year or 2 years down the road, someone is not, like another perhaps well-intentioned developer isn't going to break your view controller sequence without you knowing? And on that note, let's talk about state machines. So, what is the state machine? State machine is a pattern to represent a finite number of states and enforce known transitions between them. But there's a lot going on in this definition, so let's break it down. A finite number of states. This means that we're not trying to model the whole world. We have a constrained domain, and we only want to focus in on those few states that are important to us. Known transitions. This means that we can assign names to them. We know which states are allowed to transition to which other states. And conversely, we know which states can't transition to other states. And finally, this is perhaps my favorite word, enforce. These are enforced. There's no dynamic way of bypassing your state machine. If you want to move from one state to the other, you have to go through transitions that are known. Let's look at an example of what we mean here. Imagine the standard traffic light. We can define its states as red, amber, or yellow if you're in North America, and green. So let's list those out. Now let's think about how we move between each of these states. Green can become amber, amber can become red, and red can become green. Note that red cannot become amber, right? And amber cannot become green. So there's no arrow between those. Now, let's assume that these state transitions are caused by timers so we can assign names to them. For instance, we move from green to amber once the green timer elapses. We move from amber to red once the amber timer elapses, and so on. Now at this point, we can actually just stand back and look at the screen and admire what we've created. We've made a state diagram. We have a finite number of states, red, amber, and green, and we have predefined transitions between them. Now, this is great, right? But you're probably not here to code traffic lights. You're here to build apps. So let's go through this exercise again with something that might be a little more concrete for us. Loading remote content. Loading remote content is a great example of an implicit state machine we often have in our apps. When we navigate to a screen, we start in the loading state. We may encounter an error, which brings us to an error state. Then we can hit a button to try again, return to the loading state, and, hope it works. Eventually, we receive data from the server. If it's empty, we can display an empty state, again with a button to try again. And if not, we simply display the data. I think many of us have coded this in one way or another in our apps. And often there's not much thought put to it. But this is the perfect example of an implicit state machine. Now, how do we take a state machine like this and translate it into Swift? In my experience, the most effective way of building a state machine is in two parts. The first part is to create a state definition enum. This will represent the state diagram that we just made. It'll hold the different states and transitions, and it'll also have the rules on how your enum can change from one state to the next. The second part of this solution is creating a state machine wrapper class. This class is going to wrap the current state of your state machine and communicate state transitions to the rest of the app. This is also the component that has the facilities that your app is going to need in order to trigger state transitions when events happen. Building a state definition is pretty straightforward once you already have a state diagram, so let's start with that. Of course, since we're dealing with mutually exclusive state, enums are a natural fit. So here I have my remote content state definition enum, and I'm going to list out the possible states: loading, data, error, and empty. In addition to these cases, let's also define our different transitions. These are events that act on our state machine to cause the state to change. Again, since they are known and mutually exclusive, let's use another enum. Here, you can see that our event enum is inside our state definition enum. This is because they're intrinsically linked. Now the fun part, we define our state transitions, which looks a little something like this. We start with a mutating func. We're going to call it handle event, and when it receives an event, it's going to mutate the current state into the next state. That's why it's mutating. So in the body of this method, we're going to switch over the current value of the state, which is self, and the event. Now, this might be pretty intense, so let's focus in on a single case. Here you can see we're switching over a tuple, right, of self, which is the current state, and event. And in this case, when we're in the loading state and we receive the did receive error event, we change self to error, which means we move to the error state. And we simply repeat that for each of the transitions. Now, if you were to try to make this compile, you would get an error, which says switch must be exhaustive. There are a few ways to handle this. The first would be to exhaustively list every combination of state and event, but in our case, we're simply going to use a default label to handle all the unused cases. But now, what should we do? Well, you have a few options. The first would be, if you want to be really strict, you could crash. You could emit a fatal error and just stop your application. Though, this might be a little intense, right? I'm sure it's completely valid in certain circumstances, but in others, maybe not. But I think the minimum that you would want to have here is at least printing to the console that an invalid state transition tried to occur. This will at least alert you as you're debugging that there's something going on that you need to look into. But you could also, for example, log this using OS log. And that wraps up our state definition. Now we're going to move on to the second part, the state machine class. So let's create a class. We're going to call it remote content state machine, and it's going to have a private var called state or current state, and it's going to be equal to the initial state that we want our state machine to be in. In our case, we want to start by loading the remote content, right? So we're going to start it in that state. Next, we need to give a way to this class to communicate to the rest of the app. Now again, there's many ways that you could do this. You could use a closure. You could, for example, use a combined publisher or Rx Swift. But in our case, I'm going to use the pattern that we're all probably most familiar with, which is a delegate pattern. So here I define a delegate called remote content state machine delegate. It has a single method, did change state, and I'm going to add a weak delegate property to my remote content state machine. And finally, we need to give a way to the application to trigger these state transitions. So we can write methods on our state machine to allow these to happen. For example, in this case, we could, for example, define receive error, reload, and receive data. But what do these methods do? Well, receive error and reload will simply pass on the event to the state enum in order for it to try and do its transition. However, receive data is maybe a little bit different. The state machine class is a good place to put business logic. In our case, we're going to see if the data is empty. If it is empty, we're going to pass the did receive empty data event. But if it's not empty, we pass on the did receive data event in order to trigger the correct transition. And finally, this is, because we're using a delegate and with did set, we need to actually tell the rest of the app what our initial state is. So I'm going to add a start method that simply triggers a delegate and communicates the state of our state machine. And that's it. And now comes the part where we integrate the state machine into our app. Here I have a remote content container controller. Essentially, it's a view controller container that switches between loading data and empty view controllers based on the current state. All it has to do is conform to the remote content state machine delegate, and then when it receives a new state, we switch over it, and depending on what we get, we simply switch the view controller. This is also a good spot to trigger any side effects. For example, if we want to trigger a network request. And that's it. It makes it really simple. And here's another thing to consider. How would we go about testing this view controller? If we hadn't used the state machine, it would be really complicated to make sure that, okay, that things are being triggered correctly, that the right view controller is being displayed. But now in our case, we have a state machine that is built with a pure function that defines all of the states and transitions. I find this to be incredibly beautiful. A few years ago, I worked for a large multinational on their Internet of Things app. We had about a dozen devices to support, each with their own pairing flows and their own custom UI. In this case, we did have a state machine, but it was about 5,000 lines long and incredibly difficult to modify without introducing bugs. The kicker is that we were adding new devices like almost every quarter, so the rate at which we were causing regressions was a little unfortunate. So this got me thinking about two aspects of state machines that hadn't crossed my mind before. The first is that in some use cases, state machines tend to grow in complexity over time, right? Like you could imagine that you have a feature and in the beginning it only has like 3 screens, right? And your state machine makes sure that those transitions move correctly. But as your product evolves, or maybe as Apple adds new APIs and device functionalities, the number of states increases to something that's perhaps less manageable. But also, on the flip side of this, you come to notice that very complex state machines often have like sub-state machines inside them. So that is to say that you can take part of that complex state machine, extract it, make it its own state machine, and then hopefully reintegrate it inside to make things a little bit simpler. So to me, this kind of reveals a need for, if we're going to use state machines, the solution we choose needs to be composable. We need a solution that allows us to build big, complex state machines out of smaller state machines that are easier to reason with. So let's take our remote content state machine a little bit further. I find that the empty state and the data state are kind of similar, so I want to group these together in a child state machine. I also want to give the user the opportunity to refresh when he has data in order to either see new data or, if he's consumed everything, go back to the empty state. So let's create a new state definition and list these states: empty, data, and refresh. We'll go through the same exercise, creating an event enum for these different states. So we can trigger a refresh, we can receive empty data, or we have the receive data event like we had before. Now, once again, we have handle event. We're not going to go through this in detail, but it's there. And here's where things get interesting. Now, in our remote content state definition enum, we can remove the empty state. And instead of data, let's call the state loaded. And it's going to have an associated value. Its associated value is going to be the state of the sub-state machine. And then all we need to do is fix up the handle event method and do some event forwarding, and we're good to go. There's an example of this in the sample code at the end of the talk. So if this is something you're interested in, I encourage you to download it and check it out for yourself. All right, so let's finish up this talk with some examples. I find that the task of just discovering implicit state machines in our code is one that benefits from having a lot of examples and things to go off of. So let's check some of these out. The first is an onboarding coordinator. So for example, you could have like the login state, then some sort of app preview, and then enable location, and then like enable push notifications, for example. But in some of these cases, when you press the back button, you don't necessarily want to go back to a step that you've already done. So here, for example, for enable push and enable location, we would go back to the preview and not necessarily just the one before. Next, form validation. For example, imagine a form field in a form would start off in an empty state, then it could move into like an entering data state. As you're entering data, it stays in that state, and then once you tab out, for example, it would move into a validating state where it would try and validate the data. This is useful, especially if data is validated server-side. And then depending on what gets returned, that field would either end up in an error state where you would have to correct and go through that loop again, or it would be in the validated state. And finally, accepting push notifications. Now this is really interesting as well. So often when we want users to accept push notifications, we'll give them like a sort of priming alert. So you could show the alert. If they accept, you move on to like the system prompt for accepting push notifications. If they accept, they move to like the push accepted state, or if they decline, they move to a decline state. And there you have it. If you want to download the resources for this talk, the slides, there's like 3 projects in the sample code. You can get it at bit.ly/statemachines_sing, the URL on screen. Also, here are a few additional resources for reading more about state machines. They don't all necessarily use the same approach, but they're really interesting in order to have like a more global view of all of this. And finally, my contact information again, if you want to get in touch with me and say hi or give some thoughts about this talk, I would really appreciate it. Thank you very much, and enjoy the rest of the conference.